So on indication, many of these are shown by either ICAS indications or gauges, depending on the age of the aircraft. And so here's an example of an electrical page on, again, this is the ones you saw or you get to see when you're in the simulator, showing the ones for the CRJ200. And so again, it's a schematic. It's the ICAS schematic of the system. And so you have the two engines and the APU across the bottom, along with diagrams showing where power is going. And in this case, the line is black, but when you're using the actual aircraft, for instance, right now, the APU generator would be green. This box right here listing the voltage, frequency, and load. kVA is a current measurement, kilovolt amps. Because remember, voltage times amperage equals, or voltage times resistance equals amperage. So this is kVA. Right now this is powering, and both buses are connected because we're running off of a single generator. And then it also shows that essential bus running off the left, but it can also run off the right, those utility buses and that kind of thing. Now, the one thing that you don't see here, the couple things you don't see here, is it doesn't show external power and it doesn't show emergency power. And these ICAS displays, when you're not using external power and when it's not available, when it's not plugged in, or if you're not using the air-driven generator, then it doesn't show up. But in some of this blank space up here, you will get different configurations. If you do go to external power, it'll show up in that area. Or if the air-driven generator is deployed and has to provide power to that essential bus, that ADG bus and essential bus, it'll show up in that area as well. So again, this is normal secondary power source indication, right? The APU is the secondary power source. So how do these compare? What do we get? Oops, you can see the schematic on the left, the ICAS indication schematic is similar to the major electrical schematic that's on the right. And so you'll get this kind of thing. In the 727 older aircraft, it's all those gauges, right? We have the gauges that showed up in the different parts of it. And so right here, the gauges here don't list as much, but you do have a kilowatt kVAR. This is the kilovolt amps right down here. That is telling you what the load is for each of these. Frequency is given on this frequency panel that's off to the right. And voltage is also given on your voltage panel off to the right. You can select, there's that selector we look at to look at voltage and frequency for the individual parts or individual sections of the electrical diagram. The other thing you have here too, and these would be on ICAS, is you can see generator drive oil temp. The generators themselves, and specifically what's called constant speed drive, when we get to generation, we'll talk about that, use oil for lubrication, cooling, and as a hydrostatic system. And that you have to monitor the temperature. You don't want that overheated. In fact, there's cooling systems on the engines that keep that cool. So once we've got our electrical control, our big breakers, now we have, all those switches are going to move different circuit breakers and contactors and that kind of thing. And what we had back in the day is the flight deck, all the controls were run up in the flight deck. You look in, say, our 727, for instance, and you have that big, behind the flight engineer's panel, there's that big panel of breakers, and over the spotter or over the observer seats, there's another panel of breakers. But the one behind the flight engineer, for instance, has a lot of current running through it. It uses the main current for the buses comes up into that panel. And so you have cases where you have this diagram, what's shown here on the left. And a good example of this is the hydraulic pumps. Okay, would be hydraulic pumps as an example. So in the 727, they're wired like this. So what we have is, excuse me, we have our bus down here, our main bus, and we have, say we have, and this would be like our hydraulic pump. Say our hydraulic pump runs on 100 amps. We have a feed from our main bus going up into the flight deck to a circuit breaker panel, or to a circuit breaker that is a 100 amp circuit breaker, which will feed the hydraulic pump. Now, what it doesn't do, it's not actually, there's no switch there. We don't put a switch on that because we don't want to have this giant switch up in the flight deck. So on the flight engineers panel on the 727, there is a switch that also has a circuit breaker powering it. So there's two circuit breakers on the circuit breaker panel. There's what's called a feed breaker. That's this big 100 amp one down here. And then there's a control circuit breaker right here, which provides power to the switch on the flight engineers panel. Okay. And that switch, when you close that switch, when you move it to the on position to turn on the electric hydraulic pumps, power flows through the switch and it goes to a relay. And the relay, when the relay closes, that allows now power to flow to the pump. But what you have is you have 100 amps of current, in this case, running up to the flight deck, coming up into the flight deck, which is it's a fire, smoke, an electrocution hazard. And so what's happened then is on newer aircraft, they move those high amperage feeds, the ones that actually provide power to, say, the hydraulic panel motor or the hydraulic pump motor. Those feeds are kept down in the electrical and equipment bay or avionics bay, somewhere under the floor, down in the wing box area. And they're closer to the generation point and to the load point. So right now, power, for instance, has to come from, on these older systems like this, the 727, power comes from the bus. It has to go from, which the bus is, remember, it's being generated by the engines. It's feeding the buses. So it's coming from the tail all the way up to the nose or up to the flight deck. It's feeding that, it goes through a circuit breaker panel in there, and then it has to go, excuse me, it has to go to the pumps, which are located all the way back in the gear bay. Or in the case of this, the standby pump is all the way back in the tail again. So it's making this long loop of where you have to have very heavy duty wire. It has to be able to handle that 100 amps. It's running all the way from tail to nose, back to the landing gear, even the tail again. Which uses, that's going to lose a lot of, right? The wire alone is going to cause electrical losses. And it's very heavy, and it has the potential to, there's a lot of places it goes through structure and everything else where it can have failures and whatnot. So we're trying to get away from this. Modern aircraft try to get away from this, and they go to what's called a distributed load concept instead of a central load concept. So in the 1990s and on, the engineers that designed these electrical systems tried to move as much high current, particularly high current stuff, and nowadays move as much electrical altogether out of the flight deck. And the way they've been doing this, one of the big ways is to do what's called a remote control circuit breaker. And so here's an example of that setup. And so in this case, what you would have, the example on the right now uses an RCCB, a remote control circuit breaker. The first generation of these is instead of having the bus feed a circuit breaker panel in the flight deck for your main feeds, now the bus would feed a circuit breaker panel typically down in, again, avionics or an E&A bay or near the landing gear, wheel wells, that kind of thing, especially when, the generators are mounted on the wings. It just feeds into the wings to the center point of the aircraft, the wing ducts area. And so that's where the main circuit breaker and contactor is that supplies power to our heavy loads. Again, cooling fans and electrically driven hydraulic pumps and electrically driven fuel pumps, and on and on. Even on like the 787, that airplane's gone away from. It doesn't have pneumatic systems. It uses electrically heated leading edges for anti-ice, and it uses electric motor-driven environmental control systems, PACs. It doesn't use bleed air at all, so everything's gone electrical on that. And the main loads are down in the under the floor, away from the passenger cabin, away from the flight deck. So the first generation is we still had circuit breaker panels in the flight deck, low amperage, maybe in this case it's a 0.5 amp, located on panels in the flight deck. There's still the control switch. You might have your hydraulic pump switch in the flight deck, but that's going to control this remote circuit breaker / contactor down in an equipment bay. And so that was kind of the first generation. Okay, that's what's shown here. Click. The next one is now this front area right here, this circuit breaker and switch on our newest aircraft, particularly our ICAS, our very heavy, like our very modern ICAS. They have very sophisticated ICAS systems. A lot of them are touch screen now, or have the ability to use like a mouse and pointer system on the display. They now are, that ICAS system is now controlling the RCCB. So you eliminate the switch and the circuit breakers in the flight deck altogether. And you control these big RCs, these high amperage RCCBs from other systems up in the flight deck. From the ICAS system and that kind of thing. You might still have some switches, and again, you're not going to get rid of this altogether, but you're getting rid of as much of it as possible. And it reduces the amount of wiring, it saves weight, it reduces the current and stuff running up into the flight deck and into the cabin that could potentially cause a fire or electrocution hazard. And so we're going to this, where now it's controlled by the ICAS or the ECAM system. Okay. I do have now a video of a circuit breaker, so I'm going to try. I got to just change one thing on my sharing. Let's see if it works. See if my computer can handle it. There you go. So I'm changing optimization. We can go in and let's see if we can get this video to play. Uh-oh. I think you might have lost screen sharing. Nope. Okay. So one thing that kind of gets missed is I got a little video on circuit breaker operation, which I want you to watch because there's some question on how these things work sometimes. I apologize for any ads.
Look, Limu! Someone needs help customizing and saving with Liberty Mutual. Oh.
Employee gets fired for inventing an indestructible drone.
Right, this is a quick video about fuses and circuit breakers. This here is a fuse. You might have seen a fuse inside a plug at home. They often come, the ones that go in plugs often have written on the outside of them the current rating. How circuit breakers work? Well, there's different ways. This is the classic one you need to know about. Okay, so we'll have a wire coming in, and that wire flows around a coil. Okay, it then goes up to a switch contact and then goes out again. So this is all one bit of wire. All right. Now in reality, there's going to be some sort of iron core or something inside this coil. This coil is basically an electromagnet, so the iron core makes it stronger, and this switchy bit here is going to have something iron on it so that it can be attracted. So the idea is that as current flows, so this is then connected in your circuit, this circuit is connected in your circuit, as current flows around the coil, around here, through your circuit, the electromagnet becomes magnetized. Okay, so the electromagnet is magnetized when current flows. Now there's a little spring attached to this switch, okay, which is holding the switch closed and keeping the current flowing. But as more current flows, that leads to the electromagnet getting stronger. Okay, you'd have done this at some other stage earlier, I'm sure, that one of the ways of increasing the strength of an electromagnet is to increase the current. So as more current flows, the electromagnet gets stronger and stronger until it becomes strong enough to pull the switchy bit here down. Okay, when it becomes strong enough to pull against that spring and pull the switch down, okay, because there's a bit of iron attached to the switch which is attracted towards the electromagnet, then the circuit is open and then the current stops flowing. So when a certain current is reached, the switch is opened and the current stops flowing. And then usually there's a little mechanism, a little latch, another little latchy type mechanism here, which will then keep that open. So if too much current flows and the switch is opened, there's a little latch that keeps the switch open, so the current stops flowing and doesn't start flowing again. Then you have to go to the circuit breaker and then press a button or flip a switch, and that undoes the latch. So this circuit breaker tool, and you, when current flows through things and they get hot, if they get really hot, in that when current flows through something, it gets hot. Now, when current flows through things and they get hot, if they get really hot, they can melt. But before that, anything that heats up expands. Okay, so if you have a bit of metal and you heat it up, it expands. If you have another metal,
So I just want to real quick. So the first one is a mechanical circuit breaker. Now that he showed a second ago. Now the second part here, how they work too. This is a thermal circuit breaker. So it uses a bimetallic spring. That's what he's drawing right now, in order to open the current. So the first one's electromagnetic. The second one is thermal.
different metal, and you heat that up, it expands. But not everything expands by the same amount for each change in temperature. Let's say, for the sake of argument, that the black metal here expands more than the red one. Okay. Now, if you stick these two bits of metal together and heat them up, if the black one expands more than the red one, it ends up bending. Okay, this is called a bimetallic strip, because bi meaning two, like bicycle, okay, or biplane meaning two. Bimetallic means two metals. A bimetallic strip bends when you heat it up because one of the metals heats up more than the other. Now you can incorporate this into a switch, okay, by making this simply part of a switch circuit. So you can have your wire coming in, okay, you can have a contact here, and then that goes back out. Okay, so here's your circuit, simple as that. Okay, this end of the bimetallic strip is like bolted onto something. This end of the bimetallic strip is free to move. Okay, now when current flows through, remember the bimetallic strip's metal, so it conducts. When current flows through this circuit, okay, the bimetallic strip is going to warm up a little bit. Now, if you choose the size of the bimetallic strip correctly, then you can make it so that when a particular current is reached, say 10 amps or 20 amps or whatever, then the temperature of the bimetallic strip is sufficient to make it bend. I'll just rotate this a bit, to make it bend enough that the switch contact is broken. Okay, so when a certain current is reached, the bimetallic strip gets to a certain temperature whereby the switch is broken. Once again, these ones have a little latch, so they've got a little latch that if it comes open, that holds it open until you go back and reset it. So when the switch opens, current stops flowing, there's a little latch that holds the switch open until you go back and press a button and reset it. So this one also is another way of breaking a circuit if too much current flows. Now, what are the advantages and disadvantages? Well, basically,
Okay, so those are the two main types of circuit breakers that you'll see. And so I have these videos you can access them on e-learning. During practicals and when you do your electrical stuff, I want you to understand how these work, and I've been known to ask questions on exams where you sketch the schematics of the two types of circuit breakers, which look similar to what they had. Just real quick, the circuit breakers are put into panels. And so here's some examples of panels, where they might be. And again, we've got the big panels in the 727 behind the flight engineer and over the observer's seat. Some aircraft, they're behind the flight crew. On a 2-crew aircraft, you don't have the flight engineer, the area behind them. So they're directly behind the flight crew. They might be down on the side panels, down by like the pilot's legs, their calf and knee area, or things like that. So you'll see these in different locations on the flight deck. Okay, with that, I'm going to stop here. We'll move on to electrical sources next time, looking at generators, batteries, and that kind of thing, inverters. But we'll stop now, and I'll go ahead and do the attendance poll.